Hi, everyone. Thanks so much for joining today. I'm Chloe, and I'm with the Tri-County Regional Energy Network. And today we are joined by Judy Rachel for Load Calculation Site Survey Essentials. Before I pass things over to Judy for today's training, I have a few logistics to go over. Judy, if you wouldn't mind. Great, thank you. Please remember to keep yourself on mute for the duration of this training. If you have any questions, please add them to the chat, and we'll be pausing periodically to go over those questions. You can also raise your hand if you have anything urgent. We are recording today's training. You're going to receive a copy of the slides and the recording in the next few days into your email. We're also going to be sending out a survey. If you have the opportunity to take this survey, it really helps us out. It will only take a couple minutes of your time. And it really helps us with planning our future trainings and programming. So if you have any ideas of what you'd like to see more of, definitely fill out that survey. You can go on to the next slide. Thank you. And before we get rolling, just a few words about who we are. We are the Tri-County Regional Energy Network, aka 3C-REN. 3C-REN is funded by ratepayer dollars that we all pay into our utility bills through the public goods charge. And the benefit of being ratepayer funded is that there is no cost to those we serve. And as a regional energy network, we are able to return these dollars back to our local economy, which has historically missed out on some of these funds. Go to the next slide. Thank you. 3C-REN currently offers 6 programs focused around 3 services. These include incentives, training, and technical assistance. Today's training falls under building performance training. To see our upcoming events and learn more about our other programs, you can visit 3cren.org. Next slide. 3C-REN is proud to have hosted trainings that were attended by over 4,000 individuals up until 2023. And we're so excited that you've all joined us today to help us in our goal of creating a more energy efficient and resilient Central Coast. And with that, I'll pass it to Judy for today's training.
Great. Thanks, Chloe. Thank you so much. All right, welcome everybody. Today we're going to talk about the load calculation site survey and what is essential in terms of the data collection for the site survey to do an accurate load calculation. So this is a bit about me, and you can peruse that when you want to. I think what's most pertinent is that I was actually trained by the person who wrote the manual J load calculation procedures to be a trainer of load calculations. So that is what makes me appropriate to be giving you this webinar. The takeaways that I would like you to have for today is that you'll actually know what a load calculation is. You'll know why the site survey data collection procedure is the only way to produce an accurate load calculation. You'll be finding out what information needs to be obtained during the site survey in order to create that load calculation. And we'll also explore some of the challenges in collecting accurate site survey data. So what exactly is a load calculation? Let's all get on the same page and understand what it is before we get into, what all the data that we need to collect. So the definition of a load calculation is simply that it is the measure of energy that the heating and or cooling system needs to add or to remove from a space to provide what's called the desired level of comfort, which is really the desired indoor air temperature. So we have all these different climates all over the planet, and they range all the way from being incredibly wonderful, basically 24/7, and you could live in a tent or you could live outside. And then you've got kind of everything in between, all the way up to climates that are just completely and thoroughly inhospitable. You can't even go outside for any length of time and live. The crazy thing is that we humans choose to live in all of these different climates. I have a friend who spent 6 months working in Antarctica. He had to eat literally pounds of butter a day just to have enough calories for his body to burn to try to keep warm enough to survive in that environment. So we've got all of these different environments, and we need to be able to condition them. So we need to figure out, well, how much energy do we need to add or remove from the space in order for that space to maintain a temperature that is comfortable for us, that's different than potentially these extreme outside temperatures, down to just, kind of uncomfortable outside temperatures. So we make shelters, right? We put buildings up, which are basically shelters for us. And we need those shelters to maintain that comfortable indoor temperature. So the load calculation is our procedure to figure out, well, how much energy needs to be added or removed from that particular container, because all of the containers are constructed with different materials, with different insulation levels, with different just degrees of competency. So there's procedures that are given to us to help us figure out what this energy load is. The nationally recognized one that has been certified by ANSI is the Manual J, the ACCA Manual J load calculation procedure, and that's for residential buildings. There's a different procedure for commercial buildings. So different buildings with different occupancy loads and different kind of construction styles and different purposes have different procedures for us to figure out how much energy is needed to be added or removed to keep those spaces at that desired level of comfort or desired indoor air temperature. ACCA, the Air Conditioner Contractors of America, have come up with the most standardized and kind of defined procedure that really helps us kind of make it through the whole process of figuring out what those load calculation numbers are. ASHRAE, also very well known, has their handbook fundamentals. And that handbook gives us all kinds of references and information and formulas about the load calculation and the art of heating and cooling. It doesn't really define a specific procedure. So it's much more difficult to come up with a way to get an accurate load calculation by just reading ASHRAE's handbook, although it's incredibly informative. And then there's also when a building is actually already constructed, there are ways to do data logging and temperature and using kind of heating devices to keep the building at a specific temperature that we can then quantify and then actually know how much energy is needed. So I call that the measured performance load calculation method. And in some circumstances, that is fairly easy to do, but you do have to have the right data logging equipment and the right equipment and the right circumstances, as well as you need an actual design day to run that on. So although in some ways it can be easier than going through the whole load calculation procedure, it has very specific conditions that need to be met in order to actually even use that as your procedure for the load calculation. The whole goal of the load calculation procedure is that getting those numbers of how much energy needs to be added or removed from the space is that information that's necessary for us to select the appropriately sized space conditioning equipment. And so what happens is that you go through this whole load calculation procedure where you're basically figuring out how much resistance to all the different forms of heat transfer through a building are happening and how quickly they're happening, and therefore how much heat you need to add or remove from the space. And once we have those main numbers, which is what this dialog box over here. This is what it gets generated from the load calculation software that I tend to use. And so I have the loads for heating and for cooling. So now I know what equipment to start looking at. And that's what this is. This is the expanded performance data for one manufacturer for one piece of equipment for the heating side. And I want to size my equipment for both the heating and the cooling side. I want the equipment to work in both in all seasons, and for heating and cooling, and then for our shoulder seasons as well when we need to turn the equipment on. So I need to look at the expanded data at my design conditions and my desired indoor condition, and then that's going to lead me to being able to choose the properly sized piece of equipment. And so that's the whole goal of the load calculation procedure itself, is to give me those numbers so that I can start the entire design process of a heating and cooling system. So heat is a form of energy, and heat is transferred whenever there's a temperature difference between two materials or two spaces. The more extreme the temperature difference is, the greater the driving force is for us to either lose heat from the building or to gain heat into the building. So this is a universal law. It's a law of physics. And if anybody can type into the chat box what law of physics I'm talking about, that I'd like to see who might know what that is. And I will talk a little bit more about it to maybe give you some clues. But this law of physics is always in action, and so it's an action against our laws. I see one answer. Thank you, Richard. So we want the enclosure to contain and maintain that different energy state than what's going on outside. So in essence, we're fighting against this law. And the law basically, in summation, is that energy flows naturally from high concentrations to low concentrations, right? So heat moves to cold, wet moves to dry, high pressure moves to low pressure. And as Richard has written in, it is the second law of thermodynamics. So that's something that you guys should all know and remember, is the second law of thermodynamics. And that is just that energy flows naturally from high concentrations to low concentrations. So heat moves three different ways. It moves through conduction, convection, and radiation. So conduction is when we've got physical objects in contact with each other. We're going to get heat conduction. Convection is when heat is transferred through the movement of fluids, and water is obviously a fluid, but air is also a fluid. And heat can move through the movement of air. And then there's radiation, which is the transfer of heat as a wavelength through space. On our buildings, all of these forms of heat transfer are happening. We get radiative heat transfer hitting our roofs in particular, hitting our walls some. We get conductive heat transfer through our wall materials, through the roof. If our ceiling is our air barrier, through the ceiling materials. And then we also get convective heat movement, and convective heat movement in particular happens through infiltration in the building enclosure. So Robert, actually, that's not the first law of thermodynamics. It is the second law of thermodynamics, is the movement of energy. Heat transfer is complicated. And therefore, the load calculation procedure it's a gross simplification of both the physics and the mathematics necessary to determine the amount of energy needed in a space to provide comfort. So that being the case, what is happening is that our load calculation procedure, when we're not doing that live measured load, is really a prediction. And so we need to try to be as accurate as we can with the things that we can be accurate on, so that our prediction is as accurate as we can make it. Every dwelling is going to have a unique set of enclosure loads, but they all fall into the same categories. So we have to know where that building is located. So what's the actual local weather, the climate? And then there's the architectural features of the dwelling. Are there cantilevers? Are there dormers? What's the surface area? How is the building actually geometrically put together? We also have the construction materials and the construction techniques that are used to build the structure as part of what's going to go into our heating and cooling loads. And then there's the things that are inside the buildings. There's the types of appliances that are in the building. Many of our appliances add heat, and some of them add both heat and moisture. And the number of occupants in the building as well is going to add heat in the summer as well as in the winter, but we actually only count the heat gain in the summer and the cooling months. And occupants also add moisture to our buildings. So heating loads are the sum of all the component loads of the enclosure itself. So that's going to include the roof. It's going to include the ceiling, the walls, fenestration, so your doors and windows, skylights. There's going to be a floor load, and there's going to be an infiltration load. So all of those added up together are what's going to tell us that amount of energy that we need to actually add to the space for our heating load. With cooling, we have all those enclosure component loads, as well as those internal gains, the occupants and the appliances. So why are accurate load calculations important? They're important because it's the foundation of the entire space conditioning design process. The process starts with the load calculation, which is that manual J that you might have heard about. It's literally a book. It's a manual. And then there are other manuals to guide us through the rest of the design process. So the load calculation is the starting point for us to choose equipment. Once we've chosen our equipment, that's going to give us our airflow parameters. And then from there, we need to design our ducts and our grills. So it's an entire process, and the load calculation is the very first step of that process. And a load calculation has a direct impact on the actual operating energy efficiency of the system that ends up being installed. It also has a direct impact on our occupants' comfort. It has a direct impact on indoor air quality and a direct impact on the building durability. So we get both the sensible and latent equipment capacity when we do our load calculation. So that's one of the benefits, is figuring out both our sensible and latent equipment capacities so that we can match that with equipment. Latent load is moisture in the air, and then the sensible is the temperature that we feel. When we talk about right sizing the equipment, so choosing the appropriate size piece of equipment, what that is selecting heating and cooling equipment and designing the air distribution system so that we're meeting the accurate predicted heating and cooling loads for the house. And when we do our load calculations, we find that those of us who have not been doing load calculations over the years have really been oversizing the equipment. So with right sizing, we are able to reduce the operating costs. So if we've typically been oversizing equipment and now we get to put in smaller equipment, we're going to reduce the operating costs for our customers. And we're improving the reliability as well. We're improving the reliability of the equipment itself because it's not having all these starting and stopping, what we call short cycling. It's not turning on and off as often, so it's not stressing the motor as much. We're getting nice long run times of our equipment equipment, particularly at our design conditions. We're also improving the reliability of the various promises that we can make to people in terms of comfort, in terms of controlling the indoor air quality, and in terms of improving the building durability. So just quickly, this chart is showing down here runtime. So we're getting nice long run times when our outdoor temperature is down by our design conditions. And that's what we want to see, is that the equipment gets to start up and it gets to run for nice long cycles. The direct quote from the Manual J load calculation is that using this smallest defensible load approach to equipment sizing is going to optimize not only the system's performance, but it's also going to maximize your customer satisfaction. So that smallest defensible load approach is that we're doing an accurate load calculation. We're not padding it in any way. And then we're looking at equipment that best matches the loads. And we're given parameters, it kind of depends on what type of equipment, whether we're using furnaces and AC or whether we're using heat pumps or multi-stage equipment. But basically, it's about plus or minus 10%, of the equipment that we're choosing. So we can't get equipment in every single size. And so that's why we have to look at the load calculation, look at our performance data from the manufacturers, and match it as best as we can. The benefits include that at our design conditions, we're going to get the specified comfort and humidity control. So that's at kind of the extremes in summer and winter. And then at part load conditions, the point at which we turn the system on, but the outside temperature is not so extreme, those are our part load conditions. We're going to get acceptable comfort and humidity control. And because we're getting that humidity control, we're going to reduce the possibilities of indoor mold and mildew. And then finally, we are also able to demonstrate that we did due diligence in terms of choosing the equipment that we've installed should any kind of dispute come up, whether that's in a court of law or arbitration or just a dispute. We do have a leg to stand on to say, I went through this procedure. I did it as accurately as I could figure out. And so this is why I have very good reasons why I chose this piece of equipment to install. So on the flip side, the consequences of not making a detailed and accurate load estimate they're basically the opposite of the benefits. But in essence, the errors, whether they're accidental or whether they're an effort to actually manipulate the output to something that you think is what you should be installing, those errors are going to filter through the entire design process, and they're going to make your installation miss its mark. It's going to lead to typically system oversizing, so larger equipment. The system efficiency is going to be reduced when we install larger equipment because it's too much capacity. We're trying to either add too much energy or remove too much energy. And so that actually reduces the actual efficiency of the installed equipment. It increases the installed costs as well as the operating costs through the entire life of the equipment, and it imposes unnecessary loads on our utility grids. When we oversize equipment, we also have to make our ducts larger, or we need to add more duct runs, which also means more grills. So we're inflating the installation cost when we do that. So in this house with an oversized system, I'm needing or the person who designed this thinks that they need 3 grills in this area to condition this area, as well as air, heat, cooling going to all of these bathrooms, this water closet, just all of these rooms. When this equipment is right-sized for this house, I can condition this entire room with 1 grill. I don't need grills in these rooms. I don't need a grill in the entry area. don't need as much airflow in any of the main rooms that I would be conditioning. So equipment oversizing is adding all of these. It's more labor, it's more ducts, it's larger duct sizes, it's harder to fit in the building. Another consequence of oversizing is that the system's short cycle. So the motors are being stressed by turning on and off and on and off. And so that's what this chart is showing, that we've got a lot of short cycling going on with the system coming on and then it turning off and then it just turning on for a short amount of time and being off and on and off. So we don't want that to happen to our equipment. It affects the comfort that we can deliver. It affects the system efficiency, the operating cost, and it reduces the equipment life. At our design conditions, we're still not going to be comfortable in our homes. At our part load conditions, we're only going to get maybe marginal or just completely uncomfortable conditions in our buildings. And we're reducing the equipment's ability to control the indoor humidity when we oversize equipment, which in our dry climate, it means that we're not getting as much sensible capacity out of the equipment as we can, and we're removing too much moisture from our homes if we're getting any latent. In our humid climates, this is a real disaster with oversizing equipment in not getting that moisture removed from their climates. When a system doesn't run long enough, the coil doesn't get cold enough for it to be removing moisture. And so that can lead to mold and mildew in our homes. And then lastly, we really have no defensible reason why we chose the equipment that we chose if we cannot look back and say, look, I did my due diligence and did an accurate load calculation in terms of choosing my equipment. So that's a summation of what a load calculation is and why they're important and why it's important to try to be accurate when we're actually doing our load calculation. So let's move on to the main bulk of this presentation, the site survey essentials. So the purpose of what is called the site survey is that there is a lot of data and a lot of details that we need to collect about the structure and where it is in order to do our load calculation. So we've got to gather all the construction details pertaining to the structure. The walls, the fenestrations, and then even there's loads from equipment and from ducts, the location of the ducts, how well the ducts are insulated, and if there's any whole house ventilation. That also is going to affect our load calculation as well as infiltration. So we've got a lot of work to do in terms of getting all the data we need for a load calculation. The site survey provides the input data for the load calculation procedure, and the accuracy of the load estimating procedure is only as good as your inputs, and the input is only as good as the survey. So just like when we talk about computers, in programs, garbage in equals garbage out. So we need to do our best to have not garbage, to have good inputs in so we get good inputs out. First and foremost, maybe not necessarily foremost, but we need to know where is the building located. And latitude in particular is important because latitude has an effect on solar gain through our glazing systems. So knowing exactly where it is we're located, what the latitude is something that we really need to look up and put that into our load calculation. And the latitude determines actually how the amount of shade there might be, how the shade that's provided by any kind of overhangs actually shades how much of how much of the windows that actually shades. And that also not only depends upon the latitude, but it's the latitude also with the exposure direction. So it's important that we get the house oriented correctly on the site. So we need to get out there, with a compass, or be looking on, on Google or anything else to figure out how, what exact orientation do we consider, the front door to be, so that we get all sides of the building at the proper orientation, the proper compass direction. And with our load calculations, we basically get 45-degree increments. So we're going to figure out just how close we are to those to choose what the orientation is, since our house is considered all, at every compass point. So go to the closest orientation based on for the 45 degrees when you're choosing your orientation. Elevation is also really important. So the altitude affects air density, and the air density is important for our various formulas that we use, particularly our sensible heat formula. There's going to be a correction factor based on density of the air, and that's based on altitude as the air density changes. So since that constant affects both our sensible and our heat equations that we use to estimate the infiltration loads, the engineered ventilation loads, and any winter humidification loads, it's important for us to get that elevation correct. And once again, pretty easy to do. Get the address, get the longitude and latitude, and then there's websites that you can go to get the proper elevation. So now we kind of get to the real crux of the load of the site survey, in that we need to measure, and depending on whether you're using a software, hopefully if you're thinking of doing this, you're not going to do it in spreadsheets anymore, which is what we used to have to do. But even in the softwares, many of them have us draw the building, which is actually incredibly helpful, rather than us having to try to figure out all of the surface areas and put them in just as numbers. But even so, we still need to know all of the measurements so that when we draw the building, we're putting that building in accurately. So I'm seeing a question that's saying what software is generally used. And there's a few softwares out there. I got started on, and typically when you get started on the software, for the most part, you kind of end up tied to it. Obviously you can change, but your files are only going to be able to be opened by that particular software. So when I got started, I started using a software called Wrightsoft. Elite has been out there for almost as long as Wrightsoft. Quick Model is probably 3 or 4 years old at this point in time. And there's some other softwares with that are coming out that are still struggling with actually getting the load calculation integrated into their softwares very well. So they're still pretty iffy in terms of producing accurate load calculations. But the Quick Model, the Elite, and Wrightsoft are I think all ACCA approved as getting their load calculations pretty darn keyed in with the actual procedures. So it's really helpful to actually do a dimensioned outline of the floor plan for each level of the building. The block load is really what the load calculation is. It's the heating and cooling load for the entire building. So we need the exterior of the house. And that's actually one of the problems with some of these newer softwares that are using scanning apps to measure a house, is that they're measuring the inside of the building. And the procedures actually tell us that the block load is the exterior measurements of the building. So we actually want to include the framing member size, whether, and if it's, masonry or something, or some other materials where we have got thicker walls or a double wall system, we actually want to include all of that in the load calculation. So we're doing the exterior of the house for the true block load that's going to give us the information that we need for choosing our heating and cooling systems. Then we also want to do room by room loads so that we can size our ducts appropriately and figure out how much air, how much energy we need to deliver to each room in particular. So we've got a lot of details to put together. So basically, what I do when I first get to a site is I go around the outside and do my block load, get the exterior measurements of the entire structure. And then I go inside and I fit the rooms in to that exterior block load. And so the guidance is that I've got that exterior wall because I've already done that outside. And now when I'm fitting in my interior spaces, I go to the center line of my interior partitions. So in this drawing, if we say that this is the dining room, and then this room over here with this window is the kitchen, if I wanted to put my dining room and kitchens into for my room by room loads, I'm going to go from the exterior wall of the dining room to the center line of the partition wall, the interior wall between the kitchen and the dining room. And so then for the kitchen, I'm going to go from this exterior wall to that's the center line of this partition as well. And so that's how your measurements are meant to be so that you get your rooms fit in to your block load. This is a garage over here. So this is unconditioned space, but it's not exterior ambient space. So there's a bit of a different temperature difference that's going to be happening across this structure than there is from over this wall here. And I hope you guys can all see my little pointer. So I'm going to actually have to describe this wall because it's in all probability going to have some differences than this little bit of wall here. And the main difference being often is just the exterior siding. But even so, that is going to make a difference in the R value of this wall. And so the heat transfer across this wall. The interior of a garage may be 5/8 drywall. Sometimes it's not finished at all. It's supposed to be, but it's definitely not going to be the exterior siding that the exterior walls are. So I need to describe that differently. Then the roof over the garage, if there happens to be a second story and we've got a room over the garage, the ceiling over the garage is a partition ceiling that we need to describe accurately because it's going to add a floor load to the room that's above it. So we need to take into account and figure out, what exactly is going on with the various rooms and what do we need to describe that may be different about the various rooms. Now, the guidance tells us also that you can measure to the nearest half foot. The software that I use lets me pretty darn easily measure in 3-inch increments without kind of any additional hassle. So I'm able to do that and get my load calculations just that much more accurate by making that choice. But the procedure does tell us that if you wanted to, you could actually measure to the nearest half foot. Walkout basements are difficult to figure out often. Basements have their issues as well, but but the procedures all give us, some guidance, and there's various formulas that we have to become familiar with so that we're doing the math right to get the surface areas right. So obviously foundation walls may be entirely above grade. They could be entirely below grade, or they could be partially above grade and below grade. So any portion of the foundation wall that is exposed to the outdoor air is an above grade wall. And then the gross area of the above grade portion wall is going to equal the measured length and the average above grade height. And so let me see if I can do this quickly. No. So looking at this picture, let's see if this is going to work. It is. All right. Really what I have here and what I would need to be measuring is that I've actually got a rectangle that I need to figure out for the above grade. So that, of course, is going to be width times height. But then I end up with this triangle below that that is also above grade. And so the equation for a triangle is base times height divided by 2, which in another way of saying that is the average depth. So basically that average depth is, we're doing the equation for a triangle. So for this room, I'm going to have on this orientation, I'm going to have a rectangle. And then on this orientation and this orientation, I'm also going to have these little rectangles added to these triangles. And then for my below grade depth, I'm going to need to figure out what the depth is. And I'm just going to have a triangle that I need to figure out, which is actually the other half of basically this rectangle. So I need to figure out all of that. And then I'm going to have this rectangle on the back wall that I need to figure out. And then my entire front of this walkout basement is all above grade. So I'll be figuring out the width times the height, or the length times the width of this wall as well. So I need to figure out all of those things, as well as what the materials are. So our below grade materials are typically going to be some kind of masonry, where this wall is probably a framed wall. And so I'm going to have to figure out all of those things and describe them accurately in my data collection. So below grade walls, the depth, let's see if we can get rid of, didn't know that line was going to follow me through the presentation. Okay, so the below grade depth of a wall is determined by what's above grade and what's below grade. So if the foundation wall, say, is 2 feet deep or less, then what we're told is that that wall is classified as an above grade wall. If the foundation wall is more than 2 feet deep, then the wall is classified as a below grade wall, and that below grade area equals the length of the wall multiplied by the depth of the wall measured from grade. So in this wall, we're going to have this portion that's below grade, that's above grade, and then we're going to have all of this that's below grade. Attached spaces. So as I showed you earlier, the garage, there could be we're talking about spaces that are outside of what we're trying to condition. So if you've got a townhouse or a duplex or condos, then you're going to have conditioned spaces on the other side of some of your walls for the space that you are actually doing your load calculation for, or you may have attached garages or some other, partitioned space. And so those partitioned spaces, particularly garages, unconditioned spaces, we have what's called demising walls. And those assembly details are going to be different than our other exterior walls for the space. So you want to note any details beyond your measurements that can also determine whether you've got a conditioned space on the other side or an unconditioned space. And if you have any clues as to what the temperature tends to track, particularly in an unconditioned space, you have the opportunity to put that in your load calculation to help with the temperature difference across that assembly, which is your driving force, your heat transfer. And often you're not going to have that. So you're going to have to make an educated guess, which the softwares help you do. When we're measuring the fenestration, so the doors and windows in our wall assemblies or a skylight in a roof assembly, we want to measure the rough opening for doors, for windows, for skylights, and then daylight tubes. We have to notice that a lighting, what looks like a lighting fixture, say in a hallway or a bathroom is where they very typically are, is actually a daylight tube. If the opening, so if there were glass, say, in this door, if the glass was more than 50%, then we're going to model that as a window. If it's less than 50%, then we actually need to model that door and the window separately. And we need the details of both, the sizes and the details of both. And once again, for the most part, it's going to be simply width times height to get us the total area. And then the softwares make it very easy to be pretty darn precise in terms of total area. But if you really need to and want to, the procedures tell us that we can round to the nearest square foot. So when we're trying to figure out the rooms during our site survey, there's choices that we need to make based on the fact that we are trying to figure out both the block load and the loads of the individual rooms. So we have, closets throughout a building, and we don't necessarily need to make the closet its own separate space. So this closet I've included in this guest bedroom. It's not a big enough space for it for me to not just condition it by virtue of it being a part of this room. And then this hallway had these various linen closets as well. So I don't draw those in separately. I include them in the space that I intend their load to be associated with. We also have things like, so this is actually a pony wall, and there's, so in the drawing software that I use, there's no good way to show that this is a partial wall, but I want to think about that because I may figure that this entry being really open to this living area could potentially, depending on what loads I see, could potentially be conditioned just from this living area. And then on top of that, this space is actually completely open. So I need to know that when I'm, putting my drawing together, that I've really got, not only this whole living and dining area, but it's completely open to this entry area. So that's going to change how I potentially decide to condition this house. There's also sometimes little rooms that just they won't have enough load for me to draw them as a separate room. So I, put things in so that you could visualize what I was seeing in the field, but I didn't actually draw this little water closet as a separate room. I actually included it in the entire master bathroom. And partly that's from experience of having drawn in these little water closets and seeing that the load is not enough that I would want to directly condition it, and that I know that when I mix a room well, this area is going to be conditioned as well. So some of it's from experience. So you can definitely start out by, adding some little rooms like this. And if potentially this was an exterior wall and this was an exterior wall and there was not only a window here, but a window here, then there might potentially be just enough load for me to want to put a grill in there and condition it directly. And so I would draw it into the software so that I could see what the loads are and determine, once I've chosen my equipment and therefore my airflow, whether I need to directly condition that or not. So the software definitely helps us in terms of seeing those various things when we get our measurements right and we draw the building and put it all together and take a look at what the individual room by room loads are, as well as the entire block load. So small closets, they're usually combined with the adjoining room. Large closets, entryways, hallways, if they're 100 square feet to 150 square feet, then the procedures tell us that those should be treated as separate rooms. Just because we treat something as a separate room doesn't mean that we have to condition it directly. It just means that it's giving us the chance to look at those loads and to figure out whether they can be conditioned by proximity to adjoining rooms, or whether there is enough load in them that we really do need to put direct conditioning into them. So let's go into enclosure details. So we do our basic drawing, get our block load, the exterior of the building measured, put the interior rooms in, and now we need to go around and really figure out the description of the assemblies of the entire building. So we've got to look at the roof, the ceiling, the walls, the floors, the windows, the skylights, daylighting tubes, doors, partition or demising walls, the infiltration rate, the enclosure leakage, the duct leakage and duct system details. So whether you're planning on putting equipment on an existing duct system, or whether you're putting in a new duct system, that duct system, if it's not in conditioned space. So if we're putting a duct system in unconditioned space, there's going to be duct leakage loads, and there's going to be duct system loads. So we need to describe our duct system and where it's going to be located. And then if we have a whole house ventilation system, so not our intermittent exhaust systems, such as the kitchen exhaust fan, or if we have independent intermittent bathroom fans. I'm not talking about those source control, but when we have a whole house ventilation system, so whether that is using exhaust supply or a balanced system, bringing in outside air or causing the exfiltration of our conditioned air because we're using an exhaust only system is going to affect our load calculation, and that also needs to be put into the load calculation. So our protocols for estimating the heating and cooling loads. This is what Manual J tells us. It says to be honest and aggressive. Tells us that Manual J is an engineering tool, and it has an inherent and appropriate factor of safety, which I'll talk about in a second. And any attempt to add other safety factors or to manipulate the procedure may result in unacceptable performance, especially at our part load conditions. So there's a lot of myths out there about safety factors in the load calculation procedure. And this is a direct quote from the manual. So they are saying that there is an inherent and appropriate factor of safety, as long as we are being honest and aggressive when we are describing the assembly. And where that factor of safety comes from, I'm going to say, is mostly from two places. So first off, for example, the sensible heat equation has a constant in it. And I talked about that earlier, in that there's that correction factor for altitude from that constant. That constant is the specific heat carrying capacity of air at different altitudes. So as the air density gets less, then that specific heat carrying capacity of air changes. Now, when I do that equation, when I'm doing a delivered capacity test, say for a heating and cooling system, when I'm doing performance testing, I use 1.08 as the constant. Most of my building stock is basically right around sea level. It's very rarely above 1,000 feet. So I'm able to use the constant 1.08 for my specific heat carrying capacity of air. If I was doing it at a different altitude, I would still use the 1.08, and then I would apply those correction factors. Now, the Manual J calculation procedure uses 1.1. So they round up. They don't go all the way out to the hundredths. They round up to 1.1 and only go out to the tenths. So right there, the number of times that sensible heat equation is used throughout the entire load calculation procedure is continually giving us a little bit more and a little bit more and a little bit more of what we're going to call a safety factor, and that you're not going to have to worry that your output is going to make you end up undersizing the equipment. The other place where we end up with a safety factor is when I said things like the procedures tell you that you can round up to the nearest foot, that you can round up to the nearest half foot, depending on which part of the structure you are measuring. That right there is also additional safety factors that are going to end up giving us a load calculation that very safely predicts the heating and cooling loads, and that we don't have to worry that when we are honest and aggressive with our measurements, with our description of the assemblies, that we're ever going to end up with an undersized piece of equipment based on the heating and cooling loads that this load calculation procedure puts out. So it's not that there is, a 15% safety factor that is built into the Manual J calculation procedure, which is, I hear things like that all the time, that the procedure oversizes by, huge amounts, and or that there's a safety factor in the procedure. It's more about the way the procedure is put together that has what they're calling this inherent and appropriate factor of safety. So you should feel very confident with the numbers that come out of this procedure, that you're not going to end up undersizing a piece of equipment. And when you're honest and aggressive, you're going to get close enough that you're not way oversizing your piece of equipment either. Okay, so that was my diatribe. Roof and ceiling assemblies. When we're looking at a plan set, that in its own way, when it's new construction, is our site survey, is going through the plan set and finding all the information that we need in the plan set. And if we're missing information, then that means we need to go to whoever our point of contact is, whether that's the architect, the designer, the contractor, whoever our point of contact is. We need to get the answers to our questions so that we can accurately describe our building. So, sometimes I luck out and, I get a box like this that just, lays it out for me. I've got a standing seam metal roof. I've got, the ice and shield underneath that, which that actually is difficult to model, but and you kind of have a choice of, there's certain pieces of the assembly that you don't necessarily have to put into the load calculation, because some of it is just too hard to find out what the various density of the material is, the conductivity of the material is, the R value of the material. But we need to know what that outside surface is. That's easy to find out, whether it's the metal seam, like in this description, or asphalt shingle, or clay tile. Here I've got that it's going to be rigid foam. And what I really need to know is what the R value is that they plan on installing for that rigid foam. And they've told me R10. And then I've got some sheathing, and they're telling me it's 5/8. So once again, it's easy for me to put in what 5/8 sheathing, what the R value is of that. That's a pretty well-known factor. And then they're giving me the size of the rafters. Then on top of that, on top of the exterior insulation, they're also doing blown-in batt insulation, fiberglass batt, which to a certain extent, it's irrelevant to me what type of insulation. What's relevant to me is the R value, and they're giving that to me. So often I have to ask. Often they just will tell me that it's, X number of inches of, batt, or X number of inches of blown in. And I need to go back to them and say, all right, which are you using? John Mansfield? Are you using Knauf? Are you using Owens Corning? Because the R value is different depending upon the product. And so the more accurate that I can be, the better my prediction is of the heating and cooling loads in the end. And then they're using 5/8 chipboard, and they're intending this assembly in terms of the insulation levels to be an R48. Now, the effective R value of the whole assembly is more than the R value of the insulation levels added together. And so that's why it's important that I describe all these other pieces of the assembly so that I actually get the effective R value of the entire assembly. And so then, you could also end up with a notated drawing like this one, where I'm getting all the different layers. But so like on this, I'm being told it's 1.5 inches of rock wool. All right, so that's great. So this is where I need to go back to the person and say, okay, so I can tell you that, I think that rock wool is typically, X per R value per inch, but, what are you thinking that you're getting? We need to be in alignment here, that we're in agreement in terms of what I'm thinking that type of insulation's R value actually is versus what you're thinking you're actually going to be putting on this house. Then we get, kind of those architectural features that we need to account for. So I've got two different roof assemblies on the same room. And so I need to describe them both. I've got an asphalt vented ceiling that's under an attic, right? So I see the venting. I crawl up in the attic. I can see that it's a vented attic. And then I've got this little bay window out that is actually a metal roof, and this is a little unvented ceiling assembly. I do need to crawl up in the attic and try to get a sense of, is this actually connected through the wall system to this vented attic, which would then actually make this a vented assembly, or is this not actually connected through the wall system? And so is it actually a little unvented assembly? I need to figure those types of things out, and I need to account for them. This ceiling height is also slightly lower than the ceiling height of the rest of this room. And so I'm just trying to decide if I have time to. So that's actually this house, right? And so even though I've got it looks like all of these 3 bay windows are all drawn as if they're connected to the rooms. I've actually drawn these as separate rooms and just put a little wall, what's called a wall opening, so that they look connected. But I know that I described them with their little metal roofs and their lower ceiling heights, and described them separately so that the loads across them are accurate, which is going to be different than the loads for the rest of the room that they're actually attached to. So let's go back to where we were. Okay, so with the roofs and the ceilings, we need to look to see what is the type of assembly. And what I mean by type of assembly is whether it's a flat roof, whether it's a ceiling under attic, whether it's a vaulted or cathedral ceiling. So I need to take note of those differences. I need to note what the material is. Is it tile? Is it tar and gravel? Is it membrane? Is it the asphalt or metal? Color is also actually important and has an effect on the load calculation. So it's not hard. You don't have to describe the actual color. We basically have 4 choices when we're doing a load calculation. We want to note whether it's white, whether we consider it to be light in color, medium in color, or dark in color. So we do need to note kind of the color tone of the roof assembly as well as the wall assembly. The structure for the roof and ceiling, we need to determine what the actual structure is. Is it wood frame? Is it a wood deck? Is it a metal deck? Is it concrete? What the thickness is. So what the thickness is of the rafters, and also take note of what the thickness is of the joists if it's a ceiling under attic. Then what is the R values? What is the R value of if there's any roof deck insulation? Okay.
It did. I'm not sure how that happened.
Okay. All right. So there's the insulation level. So we have to figure out where there's insulation. Is there insulation above the roof deck? And what's that insulation level? Is there insulation in the rafters? Is it up at the ceiling roof deck, but on the interior? For high performance attics, which are becoming more and more required by code in California, at least, there's going to be the insulation in the rafters as well as at the ceiling plane. So we need to get the R values for the insulations. And then we need to describe the attic type. So whether it's a vented attic, whether it's an unvented attic, whether there's radiant barrier in the attic, whether it's an encapsulated attic, meaning that it's got the spray foam. So we need to note all of those details. And then we also need to note the ceiling finish. So, is the ceiling finish just that roof deck? Was this an attached patio that we've now enclosed and have in conditioned space, but we're actually don't actually have a ceiling finish? It's just basically the roof deck. Or is it 5/8 inch gypsum or 1/2 inch, or is it plaster? Is it 3/4 inch wood? We need to describe it and figure out its mostly and also figure out its thickness, because the thickness of all these materials determines the R value of the material, the resistance to our conductive heat movement. So what are some of the challenges? I'm sure you can kind of guess what some of the challenges are, but we get rooms with different roof assemblies in the exact same room. Often actually just describing a sloped roof assembly can have its own challenges in terms of measuring it. We need both the low end to where the ridge is, or the top of that sloped assembly. We need to figure out whether this is actually a vented assembly all the way up and over the slope part and into this ceiling under attic, or is this actually from over the slope section and down to the eave, is that actually unvented and not connected to the ceiling over attic? So we need to be able to figure that out and describe it and figure out what's our, is there insulation in this sloped area? And if so, what's the R value that we think it is, and what's the assembly versus that we probably can go up into this attic section and actually get a much better sense and see what the R value is, where the insulation is, and what the kind of components are. We also have this funky little attic space, which in all possibility is not accessible. And so first of all, we have to recognize that the exterior wall appears to be here for the building, but really the exterior wall for the interior space is over here, and this is attic. So some of these things can be hard to figure out. Then let's say that this is a living room underneath this space here. And this living room is going to have this little bit of exposed ceiling that's exposed to an unconditioned space. And so once again, we need to measure that and describe that accurately so that we're getting the load across this little bit of ceiling for this room and for our entire block load as well. Knee walls are walls that have unconditioned space on one side and then conditioned space on the other side. And those need to be measured and described. And we need to figure out whether there's any insulation in those walls as well, which depending on, whether we can get behind here and see, or often there's knee walls in our ceiling attics and we can see them. But you can see how there's certain things that we kind of have to make educated guesses and constantly be asking questions of the occupants, of the owners, what is there in our existing buildings. Dormers are difficult to measure. This is basically a 3-story house. This is an upper attic space that is converted completely to living space, and that's where these dormers are coming out. And I've got all this exterior surface area, this kind of triangle here that I need to figure out, and then the front face of it. And then this actually, like I said, is a 3rd floor space. So where this ridge is this ridge here. So figuring out how much of this wall is actually in conditioned space, and is it actually conditioned space, or is it its own kind of little attic space, as well as measuring it. So dormers are quite the challenge. As well as we've got our sloped ceiling assembly with this little bit of flat roof, which you may decide that, maybe you want to just call this a sloped roof completely. So there's some choices that we get to make kind of based on how much time it's going to take us to do this site survey. So there's little things that we may decide, okay, it's not quite worth getting that specific. If I get the slope ceiling and the insulation levels right, my load calculation is not going to be off. It's not going to affect my load calculation tremendously. And then we crawl up into an attic and we see this and we think, oh, okay, how in the world am I going to decide what the actual R value is of this insulation? So this area obviously is 0, and potentially we would be able to see where the interior top plates are. And so this might be the entire bathroom, right? We've got this bath fan in there that's not even ducted. And so I may have to put that the ceiling over this bathroom is R0. It's got, so I'm still going to describe that it's got the drywall, and I'm still going to describe the other structural features, but it's got no insulation. So I'm going to put that room has R0, whereas the room beside it, which maybe is the bedroom, I'm going to figure out, all right, so I've got fiberglass blown in, and I'm going to measure and see how many inches it is and figure out, all right, so the R value of that insulation over this room is actually this amount. Now, the best thing that we can really do when we find things like this is start to prompt the person the owner occupants that we're doing the load calculation for, that things like this are going to end up creating the need for larger equipment than what the building really should need were it insulated. I'm going to say properly, not even necessarily well, but just that the building be insulated. So I'm going to bring something like this to their attention and potentially try to sell them, let's get in our, depending on where it is, in R30 and R38 and R49, kind of, depending on where it is, what climate it's in, let's actually not have uninsulated parts of your attic. Let's not actually have a ventilation fan that's not ducted. Let's fix these things as well. And all of that's going to help my load calculation become a better number that's going to allow me to put in a smaller piece of equipment, and it's going to hold the heat in your building better. So estimating effective R value, there's kind of some guidance just out there in the world, but as you can see, when you go up and you're looking in an attic, these are probably R30 batts, but they're suspended completely above the floor joist because of this various wiring and the way they're put in. So what's the actual effective R value of, this R30 batt? How do I figure that out? And once again, the best solution is to sell a better insulation job to your homeowner. So here's one of the pieces of guidance that we have. This comes from the BPI Original Building Analyst Standards, and it's effective R values for batt insulation. And it gives you ways to try to figure out how you might want to derate the insulation level, still being honest and aggressive about what you're seeing. But if you need to, this is one piece of guidance of how to derate and try to figure out the effective R value. All right. So I'm seeing when seeing an attic like shown with various insulation, do we enter the current insulation? We always enter the future insulation that'll be installed. So if we know that that's not the condition, right? So the load calculation is for what is going to be existing, what is planned for. So if we know already that they're going to be putting in better insulation, then that's the level that we use. So I hope that answers your question, Marcus, Cooper. All right, so moving on to walls. Wall assemblies. To a large extent, it's kind of the same information. We need to be able to describe the walls from exterior to interior, the entire assembly. So when I say type of assembly, I'm talking about whether it's a frame wall, whether it's masonry, whether it's below grade, whether it's a knee wall, if it's some kind of special wall like it's a SIPS or it's an ICF wall. Uh, we need to take those details down. Then we need to figure out what the exterior is. What is the cladding of that wall? Is there none? Which often happens in garages. Is it, is it 4-inch brick veneer? Is it wood siding? Is it vinyl? Is it stucco? What is it? I did a log house once, so it was logs. And then once again, the colors. We just need to decide whether it's white, light, medium, or dark. Is there sheathing? So in our older homes, there's not going to be sheathing. In our newer homes, most of the walls do have sheathing. We kind of have to guess with existing construction what walls might have sheathing or don't have sheathing. On a plan set, we can usually see the whole sheathing schedule, and so we can put that in appropriately throughout the house. And then we also need to, especially in existing, we need to guess. Is it 3/8 inch wood? Is it 1/2 inch? Is it 5/8 inch? And so for new construction, often that's not necessarily called out on the plan, so we need to ask. We need to ask either the architect or the contractor what is going to be used so that we get that R value correct for the thickness of that sheathing. And then the insulation. Is it cavity insulation? Is it on the exterior of the framing? Is it on the interior of the framing? And then what the R value is that is intended to be installed or already is installed. And then the interior finish. Is there an interior wall? So basements often don't have an interior finish. Is it 1/2 inch gypsum? Is it 5/8 inch? Is it wood? Is it those logs for that log cabin that I did? We also need to note what the framing factor is. And so on a plan set, we're going to be able to see what the intention is, whether they're going to build 16-inch on center or 24-inch on center. In an existing structure, we need to basically ask to figure out. We usually can't see. And we don't get to know, so I walked into this building that was under construction, and even though it's 16-inch on center, this piece of wall has much greater framing factor because this is not all 16-inch on center, and we've got all this extra framing. That's kind of way beyond being of what we can take the time to model, and definitely in existing structures, we're not going to be able to see how kind of poorly that 16-inch on center was followed and how much additional framing there is. So we basically just choose between whether it's 16-inch on center or 24-inch on center. We do need to figure out if it's 2x4, if it's 2x6, if it's a double wall construction, and what that is. A house that I was doing was a double wall, and on the one hand, luckily for me, they did tear open the walls because of a rodent infestation in the wall systems. And so I never would have known otherwise that it was a 2x8 7-inch gap and then another 2x8 wall. All I would have been able to determine was kind of the overall thickness of the wall if those walls had not been torn open. So you kind of deal with what you can figure out. And then we need to figure out whether the studs whether they're metal, whether they're wood, or if the walls are actually masonry, if they're concrete, if they're brick, what are the walls, and whether that's the above grade or the below grade. We need to be attuned to the fact that not all of our walls are just wood stud walls. Some of our walls are going to have multiple assemblies. And so this room actually had a door into the crawl space area. And so I was able to get back there and actually see that I've got concrete block, and it was kind of stepped. So I had to measure to get the surface area of what the concrete block is versus the surface area of what the wood framing part of the wall was, and get those details so that that wall is modeled as both having the wood framing and the concrete block. Knee walls and partitions. So the knee walls, like I said, they're not directly exposed to the outdoors, but they do separate a conditioned space from an unconditioned space. And then we also have demising walls, or the partition walls between garages and rooms. And so we need to describe all of these walls appropriately, that they are against this partition space. And it's all the same details, but we need to note that we've got different assemblies going on in the same room. Below grade walls. You need to just, we need to scour the floor plan for all the construction assembly details. We need to figure out the structural wall thickness. We also need to determine for below grade walls and also for floors the soil type. And basically there's just 3 that we get to choose from. So we just need to get a sense of, is the soil a light dry is one description, or is it heavy dry or light damp? So that's its own description, those 2 together. Is it heavy dry or is it light damp? And then heavy damp. But we do need to make some kind of decision as to what the soil is. And then the below grade depth, if there's any interior framing and if there's any interior finish. Right, so data collection challenges of walls. So the walls often have these multiple claddings, as well as multiple assemblies, like I showed. So we need to figure out, is this a brick veneer over a framed wall, or is this actually a brick wall? And then we've also got this stucco up above, adjacent to what is probably attic, but we need to figure that out. And then I've got these doors. Are these doors or are they windows? So why don't somebody type into me based on what I told you earlier? Are these doors or are these windows? Now the windows in these doors are ellipses. And so the formula for an ellipse is pi 3.14 times, basically it's the radius of the major axis and the radius of the minor axis. So half of this length and half of this times pi is going to give us the area of this glass. Okay, and so far nobody has answered me of whether this is a door or a window. And I'm going to keep moving, but that would be a door. That's not 50% of that glass is not 50%. So I need to do a door and I need to do a window. Walking around the outside of this building, I noted that I have all this concrete. And then on the inside of the room where I am, I'm seeing all right. So it's at least fairly clear to me where the concrete is. And so I need to measure that and describe that as concrete. And I need to figure out, is this poured concrete or is it concrete block or what? I have to be able to describe it and its thickness. And then I need to come up with the surface area of where it turns into a framed wall. So those kind of measurements are often tedious, but we need to describe these rooms appropriately. And then what compass direction do I use for this rounded room? And that's where the softwares that allow us to draw things come in very handy, because I can orient the house and then I can do my best to draw this rounded room with all the windows that are at different orientations. And then the software is going to help to figure out, based on how I've oriented the whole building, what orientation to put each of these windows on and what percentage of this wall to give to the various compass orientations. But that's what's going on with a wall like this, is I've got just multiple orientations. Then there's the quantity and the quality of the insulation, which we've talked about some with the ceilings, and we have it in walls as well. And whereas we can climb up into an attic and get a sense of what's going on in the attic as existing, if that's what we're modeling, in walls, we're very often not opening walls up and not changing the wall insulation. So infrared with a blower door is one of the ways in which we can at least get a sense of what the insulate, is there insulation and how well does it seem to be performing? If we can do a visual inspection, then we do that. Probing at switch plates. So removing the switch plate, the switch plates very often are not actually caulked to the interior finish, drywall, whatever it is, plaster. And so we can pull a switch plate off and we can probe in between the switch plate into the cavity of the wall and feel if we're feeling any insulation. And often when we pull the probe out, we'll get a little piece of insulation on it so we can see that, all right, it's the pink stuff. So we've got fiberglass bats in there. So I get a sense. And then knowing what the thickness of the wall is, I can try to make, not quite a wild ass guess, but, a wild guess to what the insulation level is in the walls. This is a chart that shows how quickly the effectiveness of insulation actually degrades when it's not installed properly. So this is for bats, and you can see that with just 1% of voids and gaps or spaces, that the effectiveness of, say, an R38 bat with just 1% of these gaps or voids, the actual R value degrades to about 50%. So we want to be honest and aggressive, but we're also just making kind of a wild guess. But insulation degrades very rapidly, the R value, when it's not installed properly. This is another method that can give us an idea of the insulation. And it's kind of fun and interesting to do maybe the first few times playing around. But it gives us also a sense of the insulation level. So basically we're measuring the temperature difference between the inside wall and the inside air. And we're measuring the temperature difference between the outside and the inside wall temperature. And with those numbers, we can get an estimated R value by plotting that. So I think I have to keep moving quick here. So anyway, this is a demonstration box, and it's got insulation in each one of the stud bays, and in infrared, this is what we might see. And so the R values actually are that there's no insulation in one bay, and then the bay next to that actually has an R13 bat, and then we've got an R19 bat, which is really performing poorly, and we have an R11 bat in the last bay. The effective R value, if we used our non-contact infrared gun to figure out the actual effective R values of those bays, what we would find is that the R11 is actually performing at R14. So it's not the bat that's performing at R14, it's the fact that we've got a still air film that's at 0.68. We've got the half-inch drywall that is 0.45. Then we've got the R11 bat, which is actually performing very well because it's installed well and it has a 6 side to the air barrier. And we've got the exterior air film that's performing at 0.68. So when adding all of those up, this well-performing bay, the effective R value is actually an R14. Now the R19 bat, because it's side stapled into the bay and there's actually a 1-inch air gap between the drywall and that bat, it's only performing at an R3. So by doing those various temperature calculations, we can make an estimate if we really want to go to that extent. So if I get a 10-degree temperature difference between the inside wall and the inside air temperature, and then I have a 40-degree difference between the outside and the inside wall temperature, I can just chart that and figure out that that insulation, that assembly is actually functioning at, say, only R3 based on those conditions. So that's how that works. There's interstitial cavities and chases throughout houses. And so we need to figure out, is this interstitial cavity really kind of an empty cavity in the middle of my building? And is it unconditioned? So do I need to model this wall? This is probably an exterior wall of the house, but these other walls, are they actually partition walls, like say between a garage and the house? And so we've got, no exterior finish, and we've got our 16-inch on center, and we've got our drywall. Is that how I model it? Or do I talk to the homeowner and sell them the fact that, let's move the air barrier all the way up to the attic level and block and seal this interstitial cavity, and go block and seal around the refrigerant lines, and actually make this house better and get the insulation done properly above this. And therefore, I don't have to model this interstitial cavity or this chase into my building. Fenestrations. The attributes for fenestrations. We definitely need to know the compass direction and what room it's in. We need to note the frame type. Is it vinyl? Is it aluminum? Is it a aluminum clad wood? What's the frame type? When I say glazing panes, is it single pane? Is it jalousie? Is it block? Is it double pane? Is it triple pane? Is it a fixed window or an operable window? And what's the head height? So the head height is from the finished floor to the top of the window. What's the head height? And we're measuring the rough opening of our doors and our windows. So in my climate, we can say stucco to stucco, since we have so many stucco buildings. I know that in Northern California, there's nowhere near as many stucco buildings in other parts of the country. So we're measuring the rough opening. Internal shade devices and bug screens, they make a difference for the load on the building. So they're really important for us to describe and can quantify. So what we're looking at is, how would that internal shade device be used, or a sunscreen, at our design conditions, which is basically going to be a hot day at about 5 p.m. So like 5 p.m. in July is typically when a design day is going to happen. And so would a person, so like look at this lower windows here, would this shade actually be up this high at 5 p.m. on that hot day in July? And what I found out in this house when I was doing it is that this homeowner actually has these shades on an auto roller thing, and every single day at about 1:30 in the afternoon, I forget what time he actually has, these shades go down 100%. And then they stay down, typically through the evening or whatever. But so in this situation, those would be 100% closed at that design condition. And so that's how I would model it for my load calculation. And then bug screens. We need to take a look at bug screens. So this is a fixed window. It doesn't have a bug screen. This is actually an operable, and a fixed window in the center. And we've got bug screens on the two operable sides. And so if I'm measuring this whole window assembly as one assembly, then I'm going to say that the bug screen is 50%. So we need to figure out, and then it makes a difference whether the bug screen is interior or exterior. So we need to take note of that. If we are lucky enough to be able to get the NFRC ratings, the U factor and the solar heat gain coefficient, then we still need to definitely describe the overhangs and the bug screen situation. We don't have to be quite as descriptive in terms of the framing of the windows, and we still need the rough opening, the square inches of the window. So we still need the measurements of the windows, but we can put in the U factor and the solar heat gain coefficient for the windows. But we don't use defaults. there are tables in the Manual J procedure that give basically defaults for what the U factor and the solar heat gain coefficient is when we describe the window. So when the best we can do is describe a window, the Manual J is and the softwares at this point are directed to the table of those descriptions and pulling those R values. But if we actually the U factors and the solar heat gain coefficients, if we actually have those numbers, we're way better off putting those numbers in so that they're actually accurate, and realize that fixed windows are going to have a different solar heat gain and U factor than our operable windows, and sliding glass doors and French doors are going to have different values as well. So don't think that just because you get one that you've actually gotten them right for all the windows. So it's best if we can find the order sheet for retrofit windows in new construction. We definitely need to do the windows all separately and get the right values. And in existing homes where we just can't get any good information, we need to describe them as best as we can so that we can use the default values that are provided in the Manual J tables. Then there's external shades, overhangs, and awnings. And so when we talked about latitude and how the latitude affects how well those overhangs and awnings actually shade windows. So we need to measure the overhangs. And the ways to measure overhangs is that we need to measure the horizontal projection, which is from the wall to the lowest part of the overhang. And then we need the vertical separation, which is from the top of the window to actually the lowest part of the overhang. So that can be one of the most difficult measurements to make in the field, is getting from the top of the window to the lowest part of the overhang. And then of course we need the window height. We also need the window width. And then we need that head height from finished floor to the top of the window. And we need head heights of doors as well. With gable ends and any type of overhang eave, we go from the center of the window to that lowest part of the overhang. And that's what we need to measure in order for then the software, based on orientation and latitude, to figure out whether this overhang is going to give us any shading on that window. Skylights, a lot of details needed for skylights. We need to measure the rough opening. Often we can't get on the roof for that from the exterior, so we need to try to do it from the interior. We need to note the glazing type. So there's a lot of plastic domes out there, but whether it's the plastic dome or whether it's glass, whether it's dual pane, we need to note all of those details. The curb is the height from the roof to the kind of top of the assembly. So we need to measure that. We need to try to figure out whether it's insulated or not, and there's also a difference between what's considered small, which is kind of that 6 inches, or whether it's large, whether it's larger than that. The light shaft, we need to describe whether there's a light shaft or not, and if the light shaft is plywood, how well it's insulated. And then the sash. The sash is kind of the upper framing, and we need to describe what that sash is. Is it metal? Does it have a thermal break or not? Is it wood? Is it aluminum clad wood? What exactly is it? We need to describe all of that. So some of the challenges with our data collection for the fenestrations is when we get windows that are not rectangles or squares, we need to still figure out the area of those windows. So we need to remember our formulas, that if it's a circle, it's going to be pi r squared. If it's only half of the circle, then it's going to be pi r squared divided by 2. If it's an ellipse, then we need to do the pi times the major axis and the minor axis divided by 2. So we need to remember those formulas so we can get the area of those windows correct. And then we also get other just kind of screwy windows, right? So, this window, basically we need to break it into a triangle and a rectangle and do those two measurements and add them together to do something like that. Back to our skylights and some of the difficulties, and that sometimes we can't even see them from the ground and we can't climb up on the roof. It's just, there's no good way to get up there. It's too dangerous. It's 3 stories high, you know, whatever. But often in the attic itself, we can see the skylight shaft and we can see whether it's insulated or not. You know, if there's any kind of air barrier on it, and we can make the suggestion that that actually should be insulated and should have a 6 side to the air barrier if it were insulated, and therefore model a better skylight shaft than what we found if we can sell that additional work to improve the building. Solar tubes are pretty much impossible. At some point in time, I did scour the internet and I found some performance data for a solar tube that I found in somebody's home, but realize that you're crawling around the attic and you're going to see these metal, you know, these thin metal shafts that are really just superheat highways. So you got to figure out, you know, how exactly you want to potentially describe that. And, you know, and maybe you can also scour the internet and find some information on the daylight tube or solar tube that you find installed. Floors. Structure thickness. We need to know the structure. Is it wood frame? Is it wood deck? Is it concrete? Is it hollow core concrete? The finish of on top, whether there's no finish, whether it's carpet, whether it's tile, hardwood. The exterior conditions. Is it an ambient open crawl space? Is it a crawl space that's vented and leaky? Is it a sealed tight crawl space? Is it an unconditioned basement? So we need to describe all of that with the floors. This is a very well insulated, blown in insulation up to the, you know, from the floor joist up to the subfloor. Slab on grade. The slab on grade is where we definitely need to say whether it's over the light dry soil or that heavy damp or light damp or the heavy damp soil. Slab insulation, whether there's perimeter insulation, whether there's full under interior insulation, and in a finished building, you know, pretty much impossible to know for sure unless you have somebody that can answer that question for you. So here's some of the challenges, right? So this is, you know, this would be an awesome slab on grade with full insulation with both edge and slab edge as well as under the slab. But once this building is finished, you would never know that unless there was a plan set, an as-built maybe, or a plan set that you could refer to and get from the homeowner, or asking some questions and finding out. Because it would absolutely be a shame to model this without any of that insulation. You would absolutely be ending up oversizing the equipment more than we would want to if we didn't get, you know, something like this, a detail like this correct. Slab edge is where we lose most of the heat in a slab on grade building. So we definitely want to catch that if there is slab edge insulation. And then there's cantilevers. Typically, you know, we'll be able to see that there's a cantilever and model that this is over ambient space. So this is where we would call this over ambient open space is a cantilever. But, you know, do I have any way of knowing whether this is how that cantilever is insulated or not? In this house, there actually were openings into this floor area, and I was actually able to not only pop my head up in there, but I was actually able to get up in there and crawl this little cantilever section. So I was able to describe it much more accurately since I was able to do that. Infiltration. So with infiltration, we need to give a description of wind shielding for the building. So that includes the height of the home, how many stories the home is, the amount of wind shielding provided by adjacent structures or natural barriers. So there's these kind of 1, 2, 3, 4, 5, these descriptions that are in the manual J load calculation to to describe what kind of shielding this building typically has. And then we need to do the blower door test for the tightness of the thermal enclosure. So, of course, the effects of building leakage is that during the heating season, the infiltration is going to increase the heating load. During the cooling season, infiltration is going to increase the sensible cooling load. And then summer infiltration can also increase or decrease the moisture content of the air, the latent cooling load, depending on the climate and the indoor humidity conditions. So infiltration often is a fairly large part of the building's load. So that's one of the things that we really can do pretty darn accurately. The load calculation procedure allows 3 different methods. One is the simplified method, and it's incredibly inaccurate. You're basically just looking at the building and making up in your own head how tight it is or not, whether it's loose, whether it's semi-loose, whether it's average, whether it's tight, you're making it up. Then there's this detailed method, which is very difficult to do because you're literally counting up like all the recessed lighting, all the switch plates, all the different penetrations in the enclosure and trying to quantify them and figure out how much leakage they are causing in the building. And then there's the blower door, which is the most accurate way. It's just, yes, it's a little bit of an upfront cost to purchase a blower door, or you can get them from the tool lending libraries if you know that you're going to be out at a house doing a site survey. And we, through C3C Wren, are going to have a on-site blower door training session coming up on May 2nd. So I think that's a week from Friday. And I think Chloe's going to put a link, she did, in the chat as to how to sign up for that if you'd like to come to. It's going to be in Montecito. If you'd like to be at that live blower door day-long session where we're going to be using blower door, you're going to get your hands on it to set it up, and we're going to be testing this house that's under construction and seeing a number of different ways to use the blower door. So, for the blower door testing of an enclosure, we need to tape off the duct system because the duct leakage is quantified separately from enclosure leakage in the load calculation procedure. So we need to tape off the entire duct system when we're doing a blower door test, which is different when we're just doing enclosure blower door testing for, say, a home energy audit. So this plan set that I got from one design build firm actually has notation that at least one blower door test shall be performed after all drywall is installed and exterior wall air sealing is complete. Doesn't happen in very many plan sets, but there are some contractors who are demanding what that blower door is, and they know because of the way that they're a design build firm, so they have a very good sense at this point in time of how tight their buildings are. And so that's very helpful when I'm doing one of their buildings, is I can say to them, so, is this client really going for it? What blower door do you think you're going to get? And normally they give that number to me in air changes per hour at a 50 pascal pressure difference. So this plan set actually says this building shall meet an air tightness of 2 ACH 50 or better. So some of the collection challenges for infiltration is when you choose to not do a blower door test, that structural leakage estimation, which is, you just, like I said, guessing this house is tight, this house is semi-tight. I feel like my ears pop when I walk in the door, so it must be tight. It's a total guess and it's completely inaccurate. The component area, like I said, is you're actually trying to figure out the square foot or count of all the different penetrations in the building. Just way too difficult and time consuming to bother with when you could just set a blower door up and get the actual infiltration rate. There are some challenges with the blower door tests in that the weather could be bad. It could be incredibly windy outside, which compromises the blower door test results, or it could be raining. But we have ways to deal with that. And so the Minneapolis blower door, the Energy Conservatory actually tested and came up with the best way to test in wind, which are with these wind tees. And I have some of these to give away at the blower door training that's coming up. And with rain, you actually turn the hose basically downward so that rain, and you tape it to the exterior wall so that water cannot get into the tubing that's measuring your pressure difference with the blower door. Duct loads. So enclosure performance and duct system performance, they're evaluated separately. And of course, a tight enclosure could have a leaky duct system. There you could have a leaky enclosure and a tight duct system, and you can have everything in between. So if you're going to use an existing duct system, you definitely need to do duct leakage testing. If you are installing a new duct system, then you need to get a sense from the contractor whether they only do code minimum work or whether they do better, and come up with what the duct leakage is expected to be of that system. So we want to take full credit for duct system sealing and the insulation when those efforts are confidently anticipated or certifiable. We're going to identify duct wall insulation. So in an existing system, we need to find where it says on the ducts what the R value is of those ducts. Buried ducts in dry climates are fantastic. And so those ducts that you have even higher R value. And so we would put that in if we know the ducts are going to be buried. The ducts of this system that is being installed are all going to be buried. So we're going to put in a nice high, they're probably going to put an R38 over these ducts. And then there's ducts that are above the insulation level. And so these ducts, it's just, the R4.2 or whatever these ducts are that we're going to put into the load calculation if you're going to be, I'm going to say if you're going to be silly enough to decide to reuse a poorly installed duct system like this. We also need to describe the duct layout and the location. So the location meaning that, is it in a vented attic? Is it in the crawl space? Where are the ducts? If the ducts are in conditioned space, then the duct loads in terms of the load calculation go away. And then the geometry. So whether it's a radial system or a trunk and branch system, we need to note that for the load calculation. It's the softwares are going to figure out kind of conductive losses based on how long the duct runs probably are and how many duct runs there are. Duct loads and data collection challenges. The default for how Manual J was written really has no relationship to the way that anybody thinks about or can measure duct leakage. There's no way to look at a duct system and figure out how many CFM per square foot they're leaking. So really we need to do the duct test. And unfortunately, conductive losses change based on where the ducts are. So if ducts are up by the roof deck, they're going to be more greater conductive losses than if they're down by the joists or if they're buried in insulation. And there's not really a good way to describe that. And then there's whole house ventilation. So engineered ventilation systems that control the exchange of indoor air and the outdoor air. They increase the winter heating load and the winter humidification load. And then they also increase the summer sensible load and affect the latent cooling load. And that can increase or decrease depending on the climate. So we need to figure out if there is a whole house ventilation system, whether it is a system load, meaning that it's ducted into the heating and cooling system ducts, or whether it's got its own independent ducts so that's a space load, ventilation load. So we need to identify what it is. Is it exhaust only? Is it supply only? Is it balanced? And does it have any heat recovery, and what the percentages of heat recovery or latent recovery, if it's an ERV, and what the percentage of latent recovery is. And we need to measure that airflow so that we know how much air is being exchanged at, whether it's that recovery efficiencies or it's direct unconditioned air into the house for our load calculation. Sometimes it's just challenging managing to actually measure the airflow in a ventilation system and figure out which grills are the ventilation system. So concluding comments. Really, the load calculation is a balancing act. It's producing the accurate load calculation it's a balance between what we accurately can describe about the building assembly and making informed, aggressive, best assumptions regarding the details of the building assembly that we're unable to precisely determine. So when we can do things such as the duct the duct leakage test, or when we can do the blower door test, that those types of things are helping us to do a more accurate load calculation. When we know what the actual ventilation rate is, when we accurately describe that we've got this window at this orientation has 50% bug screen exterior and it's got this overhang with this vertical separation. When we take the time to measure those things and describe them appropriately, we're getting that much closer to having kind of actual facts and data. Whereas when we have an existing wall assembly and we kind of have to make a guess as to what the insulation value is of that assembly, or whether there's slab edge insulation or not. So it's a balancing act. And in total summary, creating the accurate load calculation, it takes time, it takes detective work, and it takes attention to detail. We need to measure what we can measure to tip the balance for accuracy in our favors, and a comprehensive site survey is essential for an accurate load calculation. So pretty much right on time. There aren't any questions. I want to thank you all. This is how you can connect with me. 3C Ren has some closing slides that we'll go through, and then we probably will have a minute or two for, if there are any questions out there. So Chloe.
Hi, thanks. Thanks for a great training today, Judy. That was really fantastic. It always is whenever you're here with 3C Ren, so we appreciate that. Before I get to my final closing slides and wrap ups, before we've got a little bit of time for questions with Judy, I wanted to plug our Code Coach service with 3C Ren. If you haven't heard about this or need a reminder to take advantage of this service, I wanted to tell you all about Code Coach, which is a free service anyone who works in the Tri-County area can take advantage of. We partner with Imbalance Green Consulting on this. They're an architecture firm in SLO County, and they provide free training, free help with any energy code questions that you might have. They're really responsive and they do a really great job. You can reach them over the phone at this phone number or online. You can submit a report. There's like a web portal for that. So if you haven't taken advantage of this recently or at all, I definitely encourage you to do so. We can go to the next slide. Thank you. And thanks again, everyone, for attending. And thanks, Judy, for a really great presentation. I hope to see you all in another training soon, and hopefully a few of you at our blower door training on May 2nd. The slides and a recording of today's training are going to be coming to your inbox in the next few days. If you have any questions about receiving learning units for this course, please email me at chloe.swick@ventura.org. We're also going to be sending out a survey. If you have a few minutes to take this survey, it really helps us out, so I encourage everyone to do so. And then we also have some exciting upcoming courses. I encourage everyone to take a look at our calendar. It's 3c-ren.org/events. I can put the link in the chat soon. And then we also, again, just want to highlight this in-person on-site blower door training with Judy Rachel on May 2nd in Santa Barbara. It's going to be in Montecito, and we hope to see a few of you there. This is a pretty rare opportunity, especially in our region. So if you are interested or want to learn more, I really encourage you to take advantage of it. And if this is something you're interested in but can't make it on that day, definitely let us know anyway, just so we know there's interest and we might be able to offer it again soon. And with that, I will pass it back to Judy to answer any questions.
Yeah, so I'm getting asked, is there a typical amount of time it takes to do an accurate load calculation? I mean, it really depends on the size of the building. If I'm, needing to do an on-site visit, but I definitely pretty much am always at a building for 6 to 8 hours to do an accurate load calculation, between collecting all the measurements, figuring out all the assembly details, all the different things, knee walls, interstitial cavities, all of that, as well as setting up the blower door test and potentially the duct leakage test. And then that of course doesn't get me the accurate load calculation. That is my data collection. And now I have to, there's other parts of the load calculation procedure that are beyond the site survey. So I need to input all of those things. I need to figure out the design conditions and a number of other things. So is there a typical amount of time for the load calculation? It probably, it can take anywhere from a quick, simple house to 10 hours up to almost 30 hours to do a typical load calculation. It just so depends on how responsive also people are with answering questions. So whether it's a plan set and architects not getting me the information and answering my questions well, and giving me the measurements that I need to just, if I get all that information, then it can go a lot faster than that. So I presented at the National Home Performance Conference in New Orleans just a couple weeks ago, and I'm wondering if anybody from the conference actually wants to say hi, that you were there as well. And I'm seeing a few people are saying thank you, so I appreciate that. And I'm glad that you sat in on this. And so somebody else is asking which software should be used. Is there any webinar about it? I've done webinars in the past on the software that I use. And you might have missed it, but I did say that RightSoft and Elite are the kind of oldest softwares that are consistently used. Quick Model is a newer software. It's probably 4 years old or so now, I think. And it uses the Florida Solar Energy Center load calculation engine. So that's a fine software to use. You're going to get, as long as you put in good data, you're going to get good data out from that software. There are some scanning softwares. There's scanning apps that are trying to be tied into the load calculation procedure. And at this point in time, the apps that I have tried don't actually do a great job measuring the building. So you have to double check your measurements. They also are having you measure the inside of the building, which means that you're losing quite a bit of square footage for the building in terms of your load calculation, since we're supposed to measure the exterior of the building. So I personally, at this point, would definitely be sticking with either the Quick Model, RightSoft, or Elite. What about CoolCalc? I don't think that CoolCalc is actually approved by ACCA. It is very simplified. It actually doesn't have anywhere near the data inputs that are necessary to provide an accurate load calculation. So I think it's supposed to be kind of simple to be used in the field quickly. And so it can give you potentially kind of a sense of what the load calculation will end up being. But I think we really need to stop talking capacity with our homeowners on that initial visit. It doesn't do anybody a service until we've done the actual accurate load calculation. And so for using the CoolCalc for you to get a sense of what you have a feeling the building's going to come out to, but yeah, it doesn't have enough inputs to give you an accurate load calculation. Absolutely, you're very welcome. Okay, so how about load calc using energy usage history? How much gas and electricity being used over time? There are some methods out there for existing buildings, but I would stick with the you need to look into it, but the actual measuring how much heat it takes to keep the building at that particular temperature on a design day is what we really need to know. That's what the load calculation is figuring out. And then from there, we're getting acceptable comfort and acceptable humidity control at the part load condition. So look up actually doing kind of what I'm calling the measured load calculation method, where you actually having a house be heated to the indoor temperature that you want it to be on a design day, and then seeing how many BTUs did that take to keep the house at this temperature at these design conditions. And that gives you the heating side of the load. I don't think I've ever actually read how they managed to do the cooling side of the load for that. So I hope that answers your question to some extent, Cooper.
Okay. If there are no more questions, we could probably end things here. Thank you so much, Judy, and thanks to everyone who's still here for being engaged in this presentation and asking great questions. I really hope that we see a lot of you on future webinars and maybe a few at our in-person blower door training. And with that, I'll just say goodbye to everyone and thanks for being here.
Yeah,
Bye.
thank you, everybody. Bye.